Hi everyone, my name is Shruti Gowda and today I am going to be presenting our paper Dual Cognitive Architecture Incorporating Biases and Multi-Memory Systems for Lifelong Learning. This is a joint work with Bahram Zunus and Elahe Arani. Deep learning has seen rapid progress in recent years, and supervised learning agents have achieved superior performance on perception tasks. However, unlike a supervised setting where data is static and independent, real-world data is changing dynamically. Continual learning aims to learn multiple tasks when data is streamed sequentially. Artificial neural networks, however, are still not effective lifelong learners. They often fail to generalize to small changes in distribution and also suffer from forgetting old information when presented with new data, which is known as catastrophic forgetting. Humans, on the other hand, show a better ability to acquire new skills while also retaining previously learned skills to a greater extent. This intelligence can be attributed to different factors in human cognition. Delving into these underlying architectures can help us formulate a new design in the quest to build lifelong intelligent agents. Multiple theories have been proposed to formulate an overall cognitive architecture. Global workspace theory postulates that human cognition is composed of a multitude of special purpose processors and is not a single standalone module. Clarion is another architecture which posits a dual system with two levels of knowledge representation. The explicit module encodes direct knowledge that is externally accessible, and an implicit module encodes indirect knowledge that is not directly accessible but can be obtained through some intermediate steps. And all these modules interact with each other by transferring knowledge between each other. Inspired by these theories, we formulate a method that incorporates some of the key aspects of cognitive architecture into the continual learning domain. We introduced a novel framework for continual learning that incorporates concepts inspired by cognitive architectures, high-level cognitive biases, and the multi-memory system. We propose DUCA, or the Dual Cognitive Architecture for Continual Learning. DUCA consists of two modules, the explicit module and the implicit module. The explicit module has a single working model and processes the direct incoming visual data. The implicit module further consists of two submodules. First is the inductive bias learner, which embeds relevant prior information. Here, we propose to utilize global shape information as the prior. This is because networks are shown to be biased towards textural information, unlike humans who are more biased towards the semantics. The second is the semantic module. This emulates the consolidation of information in the slow and fast complementary learning system. This performs a gradual accumulation of knowledge from the explicit working module. All these modules learn and share relevant contextual information and assimilated knowledge with each other. A continual learning classification consists of a sequence of tasks, and during each task, samples XC and their corresponding labels YC are drawn from the current task data. Further, for each task, a random batch of exemplars is sampled from an episodic memory. So as the first step, inductive bias or the shape filter is applied to generate the shape samples. Reservoir sampling is incorporated to replay all the buffer samples. Each of the networks in the explicit and implicit, namely the working model and the inductive bias learner, learns on its own modality with the supervised cross-entropy loss. And further, to share the knowledge between each other, a knowledge sharing objective is designed to transfer and share all the information. To provide the shape supervision to the working model and vice versa, a bidirectional decision space similarity constraint is enforced to align the features of the two modules. These are all the objective functions in DUCA. In continual learning, the domain incremental learning setting aims to assess the robustness of the methods to distribution shift. In this setting, the classes in each task remain the same, but the input distribution changes. And hence, this makes for a more plausible use case for evaluation. However, the datasets used in the literature do not fully reflect this setting. For example, MNIST is a simple dataset usually evaluated in MLP, and its variations do not reflect the real-world distribution shift. To this end, we propose DN for IL, Domain Net for Domain Incremental Learning setting. This is a well-crafted subset of the standard domain net datasets that is used for domain adaptation. This data consists of common objects in 6 different categories or domains, which is real, clip art, infograph, painting, quick draw, and sketch. In the original, the classes have much redundancy, and moreover, evaluating the whole data can be computationally expensive in a continual learning setting. The DN4IL version considers different criteria such as relevance of classes, uniform sample distribution, computational complexity, and ease of benchmarking for continual learning. So our final dataset DN4IL is succinct, more balanced, and more computationally efficient for benchmarking, thus facilitating better evaluation in continual learning. Here, we provide a comparison of our method with the standard baselines and multiple other state-of-the-art continual learning methods. The lower and upper bounds are reported as the SGD, which is the standard training, and joint, which is the training all the tasks together. We compare with other rehearsal-based methods in literature, namely ER, DER++, CO2L, ER-ACE, and CLS-ER. DUCA achieves the best performance across all the datasets in all the 3 settings. In the challenging class incremental setting, we observe a gain of over 50% over DR++. Further, we report improvements of over 6% on the sequential CIFAR 10 and CIFAR 100 datasets over CLS-ER, which utilizes 2 semantic memories in its design. Thus, the multiple module architecture in DUCA gives that additional boost in obtaining the prior knowledge from the inductive bias learner. Improvement is prominent even when the memory budget is low, for example, with the 200 buffer size. GCIL, or the generalized class incremental learning, is a more realistic setting as the task boundaries are blurry and classes can reappear and overlap in any task. DUCA shows a significant overlap on both versions of GCIL CIFAR 100. We provide some more results to show the efficacy of the DUCA method. Firstly, the plasticity stability trade-off. So plasticity refers to the capability of a model to learn new tasks, while stability shows how well it can retain the old information. And this trade-off is a long-standing problem in continual learning. Here, as shown, the other methods exhibit forgetting and lower stability and focus only on the newer tasks, which is shown with higher plasticity. CLSER does show greater stability, but at the cost of reduced plasticity. However, DUCA shows the most balance between the both. Recency bias is a behavior in which the model predictions tend to be biased towards the current or the most recent task that it learned. Again, as shown, ER and DER++ method tend to incline most of their predictions towards the class seen in the last task, thus creating a misguided bias. DUCA shows a more uniform distribution across all the tasks. Thirdly, lifelong agents, when deployed in the real-world settings, must be resistant to various factors, such as lighting changes, weather changes, and also other effects of digital imaging. To measure the robustness, we created a dataset by applying 15 different corruptions at varying levels of severity. The performances on the 15 corruptions are averaged and shown in the last figure. DUCA outperforms all the other techniques at all severity levels, thus showing superior robustness against these corruptions. To better represent the plasticity stability measure, we report the task-wise performance and the end of each task. After training each task, we measure the accuracy on the test set of each of the previous tasks. Here, an important thing to note is the accuracy cannot be just compared based on the final accuracy and the final task, because in continual learning settings, the data arrives continuously and the focus is on both the retention of old tasks while performing well on the current task. Here, as seen, the accuracy on the first task, which is the real domain, reduces to 27.6 on ER, 43.5 on DR++, and 51.1 on CLS ER after training on all the 6 domains. However, DUCA maintains the accuracy of 54.9. Thus, DUCA reports the highest information retention on older tasks while also maintaining plasticity. In conclusion, we introduced a novel framework for continual learning that incorporates concepts inspired by cognitive architectures. DUCA is a dichotomy of explicit and implicit modules in which information is selected, maintained, and shared with each other to enable better generalization. Further, we also introduced a challenging domain incremental dataset DN for IL with 6 disparate and challenging domains. The shape prior and knowledge consolidation in DUCA helps to learn more generic solutions indicated by the reduced recency bias and greater robustness against corruptions. For future work, the adaptability of DUCA serves as a robust foundation for further exploration. As we broaden the scope of DUCA beyond the image domain, a consideration is to identify a pertinent inductive bias tailored for a specific modality. For example, for the audio domain, a promising avenue for inductive bias can be spectrogram representations or phonemes. These modality-specific adaptations, guided by the intrinsic principles and mechanisms of DUCA, open the door to exciting future directions. Thank you very much.